Hello, I'm Mr. McBrien. This is SPH3U, an introduction to acceleration. Today we're going to learn how to interpret and solve some questions related to specifically uniformly accelerated motion. By the time we're done, we should have a good working definition of acceleration. So our objectives today: define acceleration, determine average and instantaneous acceleration from a velocity time graph, and calculate velocity given the time and acceleration, and also be able to do calculations based on the same equation given the other variables. So before we begin, it's worthwhile to actually spend a bit of time thinking about what acceleration is. I'd encourage you to pause this movie and, if you want to, have a look at the video. But in any case, give yourself a few seconds to think about what acceleration is in terms of words, in terms of definitions, and think about what that implies to the units involved. So please actually sit down with a piece of paper and see if you can work out what the units of acceleration should be. Okay, when you're done that, please come back. All right, so the official definition of acceleration: the change in velocity of an object per interval time, or as shown here, acceleration equals delta v over delta t. Now, we will particularly be focused on this course on the idea of uniformly accelerated motion. Most changing acceleration problems are beyond the scope of the mathematics we have at this stage in grade 11. You'll need calculus to deal with more complicated problems of acceleration that changes as a function of time. So we'll focus on the idea of uniform acceleration, and once we have that case, the parallels to our the work we've already done with graphing velocity and constant velocity, we have virtually all the tools we need to address problems here as well. So we can see that for the case of uniform acceleration, the acceleration can be found from the final velocity, subtract the start velocity, divided by delta t. And it's a trivial exercise to say that since velocity is in meters per second and time is in seconds, acceleration will have units of meters per second or meters per second squared. And many students will get caught up on these units, but it's really not that difficult to visualize, as long as you remember that second squared, really it's just meters per second. So meters per second squared, let's make sure that's clear. Meters per second squared is the same thing as meters per second. And always remember that acceleration is a vector. It has a direction associated with it. So let's jump straight into an example. Jake increases his velocity from 13 meters per second east to 25 meters per second east in 5 seconds. Let's find his acceleration. So as these problems get more and more complicated, it makes more and more sense to write down our givens and our unknowns and work from that point. So we know his starting velocity, 13 meters per second east. We know his final velocity, 25 meters per second east. We know delta t, 5 seconds, and we can find its acceleration very easily by simply applying our acceleration equals delta V over delta T equals 12 meters per second over 5 seconds, or 2.4 meters per second squared. And of course, we need to make sure that we report this as a vector quantity. So correctly speaking, it's 2.4 meters per second squared east. All right, another example. Richard reduces his velocity from 15 meters per second forward to 12 meters per second forward in 4 seconds. What is acceleration? So the exact same process as the previous problem. We have V1 this time is higher than V2. Delta T is 4 seconds. We apply the same equation, and the only difference here is because his acceleration is backward, we report a negative number. So his acceleration is negative 0.75 meters per second squared. Or we can convert his acceleration from negative terms to backward, of course. All right, so those are pretty straightforward problems, and I think many of you could have solved that, in fact, without even being given the equation. We can also rearrange this equation to find for other terms. So we can solve for any of the variables given the other numbers by rearranging the equation. So in this case, we're going to solve for our final velocity. Given our starting velocity, our delta t, our final velocity, given our starting velocity, our delta t, and our acceleration. And it's a trivial matter to rearrange that equation, of course. So, a problem having rearranged it. A ball is traveling upwards at 12 meters per second and being accelerated downward at 9.8 meters per second squared. What's its velocity after 2 seconds? So we write out our givens again. Our starting velocity is 12 meters per second. Our acceleration is negative 9.8 meters per second squared. Our time is 2 seconds. Using our rearranged equation, V2 equals V1 plus A delta T equals V2 equals 12 meters per second minus, call it 19.6 meters per second, gives us a final velocity of negative 7.6 meters per second up, or 7.6, reverse the sign, 7.6 meters per second downward. So this should give you the tools you need to go through first the graphing acceleration handout, and then move to the textbook and do a series of problems on acceleration. Tomorrow we're going to return to some more hands-on work and start to look at acceleration in lab form. Feel free to have a look at the lab before class tomorrow. Thank you.